All right, hello everyone. This is section 5.2. Should be pretty quick. We will have talked a lot about this in class, I think. So this is just kind of putting it together. So just kind of a quick reminder. What we just got through doing was a simulated sampling distribution, which is a distribution of summary statistics you get from taking repeated samples of a population. You take a random sample of size n. We did 5 rectangles. We computed the average of those 5 rectangles, average area. We did it over and over again. We displayed a distribution. We talked about what happened. So the general idea is this. The general idea is no matter what the population looks like, we'll talk more about this later, but the population of those rectangles was kind of all over the place with area. It wasn't roughly normal at all. But notice that our distribution, as the class got bigger and bigger and bigger with more samples, started to look more normal. So the basic idea is this, that the more samples we take, the more normal that distribution will become, okay? And then also, the bigger sample size we took, we only took a sample size of 5, but the bigger sample size we take, the more squished it will also get. In other words, it's hard to get an average rectangle of size 1 when you pick 10 versus when you pick 5. It's harder to get those extreme values. So they tend to disappear and it gets crunched in a little bit. So that's the sampling distribution. Just a couple things, and I'll show you an example. Just a definition here. Standard error, SE, is the standard deviation of a sampling distribution. We're going to use that term a lot. So we have the standard deviation of the population. But then once we do this distribution, we have a new distribution. It has its own standard deviation. But rather than calling it standard deviation, because it can be a little misleading, we just call it standard error. A lot of times I will call it standard deviation, so I might say standard deviation of a sampling distribution, but I'll try not to do that. But sometimes I do. And then a little definition, we're going to use these terms all year long from here on out. If a distribution is roughly normal, values that lie in the middle 95% are called reasonably likely outcomes. Okay. The outside 5%, or 2.5% on each side, those are called rare events. Pretty unlikely to get those. What this says right here, sorry, hard to see that. That's 2 standard deviations. So it's about 2 standard deviations, right? The 95% cutoffs are 1.96 z-score and negative 1.96. So it's not quite 2, but that's just about 2. So we're going to use those terms. We're going to ask what values are reasonably likely, what values are rare events. We need those definitions. And there's one other definition here. It's called the mid-range. It's just another statistic we could have taken. We took our 5 rectangles and found the average area, but we could have found the biggest area or the smallest area or the sum of the areas. In this case, the median of the areas, in this case, a mid-range, which is not quite the median, but it's kind of close. It's just the minimum plus the maximum score divided by 2. So it's the average of the lowest and the high. These are all just kind of other types of summary statistics that you can find. So real quick, just want to show you a couple of examples in our book here about what happens. I'm on page 276 to start, 277 to start. I'm going to pop it over to 278 real quick. Down here at the bottom says the histogram, and the next display shows the distribution of exam scores for 192 students in introductory statistics course. So what that is, what you see here is the population, right? So this is the population of scores, just like our population of rectangles. Notice it's skewed left. It's not roughly normal. And then what we're going to do is we're going to do some simulated sampling distribution. So it says match the histograms A, B, and C to their descriptions of the individual scores for one sample. So what we're going to do is we're going to take a sample of 30 students. That's one thing we're going to do. Then we're going to do a simulated sampling distribution of 100 samples of 30 students. And then we're going to do a simulated sampling distribution of 100 samples of 4 students. This would be very similar to the rectangle problem we did. We did lots of samples. I don't know how many. It just depends how many the class put together of 5 rectangles. So the general idea is this. The first random sample of 30 students is going to just be all over the place. Anything can happen if you take a random sample of 30. So that's going to be this one, right? Just got scores kind of all over the place. Then we're going to do the same simulation. We're doing 100 samples, but one with 4 students and one with 30. So the first thing I said at the beginning of this video was that the bigger the sample size, the harder it is to get those extremes. Think about there's not a lot of low scores, right? So it's hard to get a lower average if you take a sample of 30. If you take a sample of 4, it's more possible. So this one, Okay, notice kind of roughly normal, kind of getting there. That's the sample of size 4. But then notice what happens when we take a sample of size 30. We don't get these averages way out here anymore. It's just really hard to get those. It's a little bit more normal, but definitely more squished. Okay, so that's the general idea of distributions. They're going to be roughly normal if you take enough samples. And then if you take a big enough sample size, it'll be even more normal and then more squished also with a bigger sample size. So we're going to kind of talk about that as we go through. That's the general idea of this. The kind of last question here says the second hour class of 30 students whose exam scores are part of the data set had a class average of 86. The instructor says that that's just a random assortment of typical students. Do we agree? In other words, she's trying to see if her class is better than an average class. She just says, no, it's just random. So an average of 86 of a sample size 30. If you look at this distribution here, these are the ones where sample size 30. Notice, almost impossible to get an average of 86. If we just go up here, take a random sample of 30 students, almost impossible to get an average of 86. You'd have to get all scores kind of in this region here. So it's not likely that her class is just random because it's a rare event. Remember, my idea is reasonably likely. Would that have been reasonably likely? I do not think that would have been reasonably likely. We could figure out that math. That's what we're going to do in the next section. We're going to figure out that math. Right now, we're just looking at that picture and saying, no, it does not look like it's in the middle 95%. It's in the actually outside 95%. So that's kind of the idea of where we're headed. Really, the most important thing to know just right now is about it getting more squished and more normal the bigger the sample size is.